Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Today our group will present about nuclear fission as a sustainable energy source. First, what is nuclear fission? Nuclear fission is a process where two light atomic nuclei combine to form a heavier nucleus while releasing a very large amount of energy. This is actually the same reaction that powers the sun and other stars. Scientists believe that nuclear fission has great potential to become an important energy source in the future because it can produce huge amounts of energy with less environmental impact. Our group chose this topic because nuclear fission has many advantages as a sustainable energy source. Firstly, it has an abundant fuel supply. Deuterium can be easily extracted from seawater while tritium can be produced from lithium inside the reactor. This means the fuel supply could last for millions of years. Besides that, nuclear fission is also carbon-free. The process does not release carbon dioxide or greenhouse gases into the atmosphere. Its main byproduct is helium, which is an inert and non-toxic gas. Therefore, fission energy can help reduce global warming and environmental pollution. Next, nuclear fission has inherent safety features. A nuclear meltdown like the Fukushima disaster is physically impossible in fusion reactors because if the plasma becomes unstable, the reaction automatically stops within seconds. Lastly, fission produces minimal radioactive waste compared to nuclear fission. It does not generate high-level, long-lived radioactive waste that requires storage for thousands of years. For our methodology, the information used in this presentation was collected through secondary research. We refer to trusted websites, scientific articles, ebooks, and e-journals to ensure that the information is accurate and reliable. Thank you.
Hello everyone, my name is Muhammad Hamadi. Today I will be covering the part about challenges and solutions as well as applications in daily life. Now, as we all know, nuclear fusion reactors are still in the development stage. They are still an experimental idea. So, naturally, we are faced with many challenges trying to utilize it fully. One of the main challenges that we are faced with today are the high construction costs as well as the maintenance. For one, a fusion reactor needs at least more than a few millions of ringgit to construct a proper reactor without cutting costs. Now, one of the solutions to this is to build a small design of a fusion reactor. A smaller design would lead to a significant reduce in cost production as well as maintaining the benefit of the reactor. Now, the second challenge that we're faced with is the source of tritium is not abundant. There's not many left on Earth. We need to either find a way to reproduce it or find it somewhere else. Now, tritium is one of the main components in fusion reaction. Now, they are naturally really important for us because we need it to make energy. The main solution to this would be to line the fusion reactor core with lithium breeding blanket. Now, neutrons ejected from the fusion reaction will react with the lithium blanket. When they react with each other, this will produce helium isotope 4, and as well as tritium. So not only we can use tritium, we can also reproduce it the same way at the same time simultaneously. Now, onwards to the third biggest challenge would be we need to find a way to provide the fusion reaction with heat energy. Now, in fusion, we need a lot of energy to supply the two elements that are colliding for fusion. Now, the two elements here are deuterium and tritium. If they want to fuse together, we need a lot of heat energy for that. Now, if we're using normal tools like lasers and normal electromagnets to heat up the substance, it won't be enough, or it will be enough, but instead of producing positive total net power, we will be producing negative total net power. That means we're actually losing power rather than gaining it from fusion reactor. Now, one of the experimental solutions to this is to invest and design and advance high temperature superconducting magnets to supply this reaction with enough energy. We would supply it with enough energy but not too much energy. Basically, we would find the balance in things so that it has the amount of energy needed for the fusion reaction to occur but not too much energy use, that the total net power will become negative, so that we're actually gaining some benefit from it.
Hello everyone, my name is Danish. Now let's take a look at the actual physics of nuclear fusion. So basically it is a nuclear reaction where two light atoms, they fuse together at extremely high temperatures and speed to form a heavier nucleus. So surprisingly, it is the same process that powers our sun and every other star in our universe. So for energy production on Earth, scientists focus mainly on two specific hydrogen isotopes, which is deuterium and tritium. Why? Because currently it is the easiest fusion reaction that we can achieve using our current technology. Because deuterium can be extracted from seawater and tritium can be produced from lithium, so the source is very abundant. So the energy released during fusion can be explained by Einstein's equation, E equals mc squared. The equation shows us that mass and energy can be converted into each other. So the E stands for energy, M is for mass, and c squared equals speed of light squared, which is a very large number. It means that even for a very tiny loss of mass can be converted into a huge amount of energy. So in our case, which is nuclear fusion, when the nuclei combine, the total mass after the reaction is slightly smaller than before the reaction. So that small difference in mass is released an energy, which is why the fusion can produce such powerful heat and radiation from even a little fuel. Today, scientists use two methods to test fusion. The first one is magnetic confinement fusion. Basically, they use a big, strong magnets to hold hot plasma in place. This is being done in ITER in France. The second method is inertial confinement fusion. So they use powerful lasers to compress a tiny fuel pellet until the reaction of fusion begins. This is done at the National Ignition Facility in the United States. And surprisingly, in 2022, they achieved net energy gain in their experiments. So this shows us that fusion is becoming a real future in energy source.
Hello, it's me again. Welcome to application in daily life for a nuclear fusion reactor. Fusion reactors produces a lot of fresh water because they boil seawater into steam, and we can use the steam to turn them into fresh water source. Now, we can use this abundance of fresh water produced by the reactor for our daily life, like showering, brushing your teeth, and drinking. It's not radioactive at all. Now, the second thing that we can use it for is we can use it as a production of clean hydrogen. Energy generated by the nuclear fusion reactor can be directed into facilities that focuses on electrolysis of water. Electrolysis splits water into hydrogen and oxygen, and we can utilize the excess hydrogen to be used as fuel cell for vehicles. In today's, there are vehicles being developed to use hydrogen as fuel. We can use those as a main transportation for everyday use.
So now let's take a look at three big issues that shaping the nuclear technology today. So the first is big technology and AI need a massive amount of electricity. So basically, wind and solar are not always reliable enough to run the data center for the entire day. So technology companies are turning to nuclear power for a steadier and constant energy. And then the second is, currently we're having a fuel problem. The newest reactor need a special type of uranium. We call this HALEU, HALEU. Because of Russia has historically controlled most of this market, the rest of the world is now facing a huge supply shortage. And then the last is small modular reactor. Small modular reactor, or SMRS, are finally happening now. Instead of building giant and expensive power plants from scratch, these smaller reactors are built in factories and shipped directly to the site. This year, we are seeing them move from just ideas on paper to a real-world project. Together, these three changes are completely reshaping the industries of nuclear technology.
Okay, next I'll talk about the career opportunity in nuclear fusion. There are several career options in this field. For example, you can become a nuclear physicist where you study atomic reaction and energy production. You can also work as an energy researcher, focusing on developing cleaner and more sustainable energy source. Besides that, there are also plasma physicists, where you study plasma, which is very important in nuclear fusion. And lastly, there are engineering role in fusion reactor, where engineer design and build fusion system. Now let's look at the skill needed. First, you need a strong understanding of physics, especially modern physics and also mathematics. Next, technical skills are important, such as programming using Python and data analysis, which are used for simulation and experiments. Other than that, soft skills like critical thinking and problem solving are also important to deal with complex challenges. Now, I will talk about the importance of continuous learning. First, it helps support global energy goals because nuclear fusion can reduce carbon emission. Next is help improve safety, where scientists can make reactors safer and manage risks better. It's also help improve efficiency and performance by increasing energy output and reducing energy loss.
Let's take a look at the four main challenges holding back nuclear energy today. And the most important is how we are solving them. So the first is the fuel supply bottleneck. We need a lot of more fuel. So the solution is now by investing billions of dollars to build a local uranium facilities. The way is we don't have to rely on the other countries. And then the second is old rules and red tapes slows everything down. To fix this, major agencies like the NRC and IAEA are working together to streamline and update their regulation so things can move faster and safely. And then the third is building a giant nuclear plant usually leads to huge delays and financially risk. So the solution what? We are shifting to small modular reactors or SMRs. Because they are built in factory, they are safe a ton of time and money. And then the last is extreme radiation wears down reactor parts over the time. To stop this metal breakdown, scientists are inventing super strong metals and even testing advanced ideas like liquid metal walls. By fixing these four issues, we are making the future nuclear energy a reality.